Welcome back to the lab. It's time to kick off a new project, codename Project Darwin. We're going to talk about the goal and vision of this project, talk about the value of a proof of concept phase, and introduce the system architecture for Project Darwin. This is going to be a big step in our journey of learning about electronics. In our previous project, the Plant Light project, we had some fun. It was a great way to get our feet wet. We got to dive in, learn some things about current regulating switch mode power supply, create a simple switch mode power supply controller in LT-Spice using comparators, lots of great intermediate circuit concepts. If you have a few hours to kill, check that series out. It's all in a playlist for you. If you don't have enough time for that, check out the compilation video at the end. It's a great project that serves as a great example for DC to DC power conversion without risk of electrocution, and it allowed me to learn a lot about modeling for 3D printing. That was an old project. What about our new project? I've been feeling a little silly about how I got all excited about the Plant Light project and I didn't define my requirements properly. Due to a combination of this excitement and a rush to get the project done, I designed the LED circuits before defining our brightness requirement, and then we ended up with a lamp that didn't meet our main requirement. To try and rectify that situation, I began thinking of projects that would demand proper requirements. Something difficult enough that doing it wrong would be a fire hazard. Something exciting, electrifying even, the kind of project that your average Joe couldn't get right on the first try. After a few weeks of indecision, I settled on a project that gets me excited for a few reasons. First, I'm going to need to buy the new lab equipment for the shop, so win. Second, if I make a mistake, it'll blow up and look really cool on camera. Side note, I'm going to try and contain my excitement using good engineering practice to reduce the risk of looking really cool on camera. Third, this is the kind of circuit that can be difficult to get custom built and bring to market, just due to the complexity and cost of the system, regulatory restrictions and requirements, and what a consumer is willing to pay. Since the value proposition for designing something like this from scratch isn't there, it's unlikely I'll ever get to design one where someone will pay me to do it. Lastly, this project brings up a few topics that we haven't really talked about before. Isolation, AC to DC conversion, what happens when a design gets scaled up from low power to high power, FET versus BJT, the list goes on. In other words, this is the kind of project that is fun, interesting, different, and people probably won't pay me to do. This sounds like great project fuel. Speaking of things that sound great, the project and circuits described in, resulting from, or associated with this video series are meant for entertainment purposes only. These circuits are not designed to be run unattended outside of a controlled environment. The designs are not registered for use or sale in any country. The resulting designs are not listed with any safety agency nor tested for compliance with radiated or conducted emissions regulations. There are lethal voltages used in this project, and you should never, ever attempt to duplicate it without a proper education and certifications from a local authority. To that end, nobody should ever plug any of these designs into any power source, ever. There is some serious danger involved with this project, and you should not attempt to duplicate it at home. That out of the way, I've made the decision to hide what we're building until I absolutely have to tell you. In case, we find out I can't actually. Okay, fine. We're building a power supply. There. I said it. I might have intentionally misspoken and left out some details, but I said it. So what is a proof of concept phase anyway, and why do we need it? Well, this is very simple in concept. Let's say you're changing something big in a design, like changing from a microcontroller to a different vendor. If you're making a radical change like that, the result will be spending a month or so designing a new board to fit that micro on it. If it turns out that after you spend that month building the board that it doesn't actually meet the needs of your design after you spent that month making the new PCB, well, that wasn't a very efficient use of your time. How can we prevent this kind of useless, wasted time? This is where the proof of concept phase comes in. Whether it's a small board you design yourself for an off-the-shelf development kit, or some combination of the two, using simple hardware to simulate the part of your system architecture to remove risk from a larger design, removing risk from those large design changes is what the proof of concept phase is all about. The better you understand your system before you try to design, even put a trace on that new PCB, the better. To restate in industry standard terms, the proof of concept phase exists to de-risk critical circuits in a design through rapid prototyping and engineering confidence testing before entering a formal design phase. Practical example time then. What does the proof of concept phase look like for Project Darwin, a high-power power supply? Well, our primary objective for this proof of concept phase is to develop a control system to achieve voltage regulation regardless of the load. There are a few key elements that should be tested in this phase of the project. First of all, that real-time control system implementation and software that then runs on a microcontroller, both halves of that can be tricky. An implementation of a standard UPS protocol over USB or TCP/IP to get runtime information integrated into Windows and Linux for automatic shutdown. Yeesh. And third, the power output stage for the system. These three items are the largest risks for Project Darwin, and here's why. Shoot-through is a known Achilles heel of the architecture we selected for the power output stage. Second, I don't have a lot of experience with implementing the software for higher level interfaces like TCP/IP and USB on a microcontroller, and I have no experience with the specific protocols or standards that are used to translate the runtime information, like power, current, and runtime remaining, into something a computer can understand. Running the control loop and tuning it is fairly easy, but there's a lot of bugs that can be introduced when shifting from a theoretical control system to a real one, whether it be delay introduced by your sensors, sampling error, or inconsistent sample times. When doing the original architecture planning for this proof of concept phase, one of my assumptions was that there'd be an off-the-shelf controller for every switch mode power supply our system might require. And that assumption turned out to be false. Well, this is because what we need the final output stage of the power supply to do is not as simple as a fixed DC power supply. And what this means for the project is that we'll need to sample the voltages and currents that need regulation, roll our own control system, and then use a microcontroller to sample our sensors and ultimately serve as the PWM generator. Now, while this work is a bit of a hassle at the moment, it does provide a few features that may turn out to be very useful in the future. For now, let's consider this to be a simple voltage regulator. As long as we already need to implement a microcontroller for running this control system, picking a microcontroller with good hardware abstraction and native USB support doesn't really require much of an upgrade. For this project, we'll be testing out the STM32 series of processors made by STMicro. I have a div kit here, and we'll try to get everything running pretty quickly. Based on my research, the libraries and examples from ST should make the digital and software parts of this project really quick. Now, that'd be great, because I want to keep my focus on the awesome analog work ahead of us and the control loops we have to tune. We'll be implementing a very special type of voltage regulator, which, based on some preliminary calculations and simulations, it'll rely on energy sloshing around between two LC low-pass filters. The plot of voltage on either individual side of the load looks completely crazy, but the math works out when you compare the voltage across the load, ignoring their respective voltage to ground. The voltage comes out to the input voltage times the duty cycle percentage with a very small ripple, just like we'd expect. We'll build and tune our PID loop to optimize voltage regulation performance, but the load of the system isn't well defined, so that'll be a little tricky. It'll be an interesting challenge because we don't know if the load will be switched, constant, inductive, resistive. We have no control over the load. What we do have control over is defining an acceptable range of performance and ensuring that the converter will stay within that acceptable range with all reasonable loads. In the coming videos, we'll walk through many different aspects of the project, such as the specific topology of switch mode power supply I chose for this proof of concept effort, and also why that topology was chosen. We'll design our circuit, buy some parts, and get a control system up and running. Let's wrap up by talking about the general architecture for this project in more depth. Our system will first take power from an endless supply, such as a generator or mains, to the house. This will then be converted from AC to DC, which can be used for the final output stage. There will be a supplementary DC power input for something like a solar panel that will allow feeding the output stage from a secondary power source. This will all be controlled by the microcontroller, well, at least a microcontroller, potentially the one that manages the output stage, while a secondary micro handles the higher level functions, such as the runtime remaining, handling the user interface, and any other time-insensitive functions that need to happen eventually, but not necessarily synchronized to the output. Naturally, all of this can't all happen at once, so we'll have to split the project into parts. We'll start with our hardware design. After our hardware is finished, we'll order the fabs and parts. While we wait for those materials to arrive, we'll begin digging into the control loop, starting from a generic PID parameter and dialing that in to become something more useful. Once we have that control loop tuned, we can hook the dev kit up to our design. With this complete, we'll test our first attempt at creating a voltage regulator algorithm through line regulation, load regulation, and step transient testing. We'll take that algorithm, improve it, and then modulating the voltage reference to see if we can get this voltage regulator to output a more complex waveform is a pretty small step. Since we have a software voltage reference, once we've achieved voltage regulation, we should be able to create that waveform of arbitrary form while outputting a large quantity of power, as long as the frequency of that output signal doesn't get too large. There is one specific waveform I have in mind right now, but I'm getting a little ahead of myself. Our proof of concept test platform will be designed to support at least 300 watts of output power. Now, I am very excited for this project. New lab equipment, new challenges, neat analog power filters, control systems, dangerous voltages, and it's just going to be a lot of fun. I hope that you stick around for the rest of Project Darwin, where we'll be in the shop for a few weeks to make something awesome. Remember, if you have any questions about your project, send me a tweet at EEforEveryone with #researchhour so I can see your question. When we have a few topics to talk about, I'll set up another live stream and we'll talk about them. I think that we can both learn a lot from Project Darwin. If you think that Project Darwin sounds cool and you can't wait to see more, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Thanks for watching EEforEveryone, and thank you for staying till the end. Bye!